let's take a look at section 3.4, where we're looking at zeros of polynomial functions. There are several important theorems in this section. Let's briefly go over those. The first one is the rational roots theorem. And this theorem basically says, if my function is an nth degree polynomial that has integer coefficients and P over Q reduced to lowest terms is a rational zero of the function, of this polynomial function, then P has to be a factor of the constant term, which we call A sub 0, and Q has to be a factor of the leading coefficient, A sub n. And that's a really important theorem. We're going to look at an exercise that illustrates how we use this. The next important theorem in this section is the fundamental theorem of algebra. And that basically says if my polynomial f of x is an nth degree polynomial where n is bigger than or equal to 1, then the equation f of x equals 0 has at least one complex root. So in other words, one solution that's a complex number. And remember, real numbers are complex numbers. They're just a special type of complex number. Then we have the linear factorization theorem. And that basically says if I have an nth degree polynomial where n is 1 or bigger and the leading coefficient of that polynomial is not 0, then this function can be written as the leading coefficient times a series of linear functions or linear expressions. A sub n, remember, is my leading coefficient. That can be multiplied by x minus c1. That factor is multiplied times x minus c2, times x minus cn. So c1, c2, and cn, so these n constant values are complex numbers. They could be real. They may not be different from one another. So an nth degree polynomial can be expressed as the product of a non-zero constant and n linear factors, where each linear factor has a leading coefficient of 1. So we'll look at how to use that theorem as well. So this is a really important theorem. All of these theorems are important. The linear factorization theorem is extremely powerful in solving and rewriting polynomial functions. Descartes' rule of signs basically says if I have an nth degree polynomial with real coefficients, I want you to notice the condition here, and I want to go back for a minute to the rational zero theorem. Notice in this theorem your coefficients are integers. In the Descartes rule of signs, the coefficients just need to be real numbers, so those don't have to be integers in this case. So what this theorem allows us to do is to understand how many positive real number zeros the function may have and how many possible negative real zeros the function may have. So let's see what this says. It's a very interesting theorem. The number of positive real zeros of this nth degree polynomial is either the same as the number of sign changes of f of x, or less than the number of sign changes of f of x by a positive even integer. If f of x has only one variation in sign, then f has exactly one positive real zero. The number of negative real zeros of f is either the same as the number of sign changes in f of negative x, or less than the number of sign changes in f of negative x by a positive even integer. If f of negative x has only one variation in sign, then f has exactly one negative real zero. So this is fascinating. It's quite complex how such a rule could be arrived at. And we're not going to concern ourselves in this class with how in the world did Descartes come up with this rule of signs. We're just going to look at how do you use this and the other theorems that we've discussed to solve a polynomial equation. So let's go to exercise 46 of this section, and let's solve the given polynomial equation by using the rational zero theorem, Descartes' rule of signs, and possibly the graph of the polynomial function shown by a graphing utility as an aid in obtaining the first zero or the first root. And we're actually going to also be using the other theorems that we talked about, the linear factorization theorem, as well as the fundamental theorem of algebra. We're also going to use those as well. The use of those, though, is so automatic that they weren't actually mentioned in the instructions. All right, so let's take a minute and remember the rational zero theorem. And that basically says that I can look at the leading coefficient and the constant excuse me, to find out the possible rational roots of this polynomial. So P over Q is the rational root. P is either a factor of the constant, and Q is a factor of the leading coefficient. So let's apply that to this equation. All right, so we see that n is 4. This is a fourth degree polynomial. So a sub 4 is the coefficient of x to the fourth. So a sub 4 is 1. A sub 0 is negative 8. That's our constant. P over Q is a possible rational root. So P has to be a factor of negative 8. So P could be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. Q has to be a factor of 1. So the only possibilities for Q are plus or minus 1. So that makes it easy. So in other words, P over Q is going to be plus or minus 1 over plus or minus 1. So that's merely a plus or minus 1. So in other words, we're going to get all the numbers that are in the numerator, since our denominator only possibility is plus or minus 1. If there were other possibilities in that denominator, we would, so in other words, we're always going to have plus or minus 1 in both the numerator and the denominator. But if there were other possibilities in the denominator, each numerator would have to be put over those other possibilities. And if those give us any numbers that aren't already listed, then they would be added to the list. So an easy thing to do here is to use a graphing utility to see which of these is possibly a rational root by looking at a graph. Now, the thing to remember is that a root is an x-intercept of the function. So if I am trying to find zeros or roots, I am looking, when I look at the graph, I'm looking for the x-coordinate of points of the graph that lie on the x-axis. So one of the things I want to show you is that if you are on the MCTC campus and you're using one of the computers there, you actually have access to a program called Mathematica if you're in one of the computer labs. And this is, if you are on a computer and you click this Microsoft symbol and you hit all programs, Wolfram Mathematica should be listed on all of the computers in the computer labs. Once you open that, select Wolfram Mathematica. Right now that's version 10.1. That's forever changing, so that may not always be true. And Mathematica will open up. This is a powerful software system that I've used for many years, but it does take a little bit of getting used to, but I'm going to show you how to use it to graph. And so essentially I'm going to tell it here that I want to open a new document, which is going to be what Mathematica calls a note. And I'm going to magnify this by clicking on this the arrow next to the percentage, and I'm going to tell it to make it 200%. And that gives me something nice and visible. And a simple thing that you're actually looking for, or that you can use, is the plot function. Now in this 10.1 version of Mathematica, once I click the name of one of the Mathematica functions, it simply shows up as in a list. Any function that has what I've typed in it will show up. I want to use the plot function, and Mathematica uses square brackets when I'm using a function, and inside of this function I'm going to put our polynomial, which is x to the fourth minus x cubed plus 2x squared minus 4x minus 8. If I click on palettes and select Basic Math Assistant, that allows me, and I'll pull this over so that you can see it, that allows me to make things look like they're supposed to look. So I can put in exponents. This is very similar to the palette that you use in my math lab, to put in exponents and fractions and have them formatted nicely. So notice how I'm just typing in my f of x, my polynomial, and the only thing I need to, that's absolutely required for a function of a single variable here, is that I give a range of x. And a lot of times it's hard to know without just putting in something to start with what a good range is. So I'll go from -8 to 8. And I hit Shift Enter. So I held the Shift button and hit Enter while still holding the Shift button to get Mathematica to run this. So it did give me some output. And it one of the things I see here is that I'm so zoomed out that I can't see where the x-intercepts are. So what I'm going to do is I'm going to give this a plot range, and I'm going to tell it to, so this is giving a range of y values. And notice what I typed in here to get this arrow. I typed the dash and then the shift button of the where you would get the period or the the period end of a sentence. And when I type in something else, that turns this into an arrow. So I need to use a brace, and I'm going to tell it to go from -4 to 4 with the y values. And things have to be typed exactly like I'm showing here. Anything that's capital has to be capitalized. Anything that's a brace has to be a brace. Anything that's a bracket has to be a bracket. If you violate this, it won't understand what you're talking about. So when I put my range of x values in, that has to be inside a pair of braces. This is a computer program, and it is intelligent only to the level that it has been programmed. So if you use a parenthesis where you're supposed to use a bracket, it's not going to understand what you're talking about. So notice by changing the plot range, I'm able to see, and this saves me a bunch of work, I'm able to see that -1 and 2 are actually zeros. So in other words, my list of possible, so now let's leave Mathematica and let's go back. We see that of our possible rational roots, -1 and +2 are actually numbers, real number values, rational number values that are roots. So from our graph, we see that x equal -1 and x equal to 2 they're actually solutions to the equation. They're roots of the function, but solutions to the equation. So I'll just abbreviate solutions. All right, so let's test those out and see if that's true. So let's raise -1 to the 4th. We want to make sure we haven't misinterpreted the graph, but we know we haven't because the rational roots theorem told us what the possibilities were for rational roots. And we saw that 2 of our possibilities, just by looking at the graph, were actually rational roots. And so if you have access to the MCTC campus during the hours the computer lab is open, then you will be able to use Mathematica. Otherwise, you can use a graphing calculator. You don't actually have to use a graphing utility in this problem, but it sure speeds things up if you have one. All right, so -1 is raised to the 4th, and I get 1. -1 to the 3rd is -1. And remember, that was being subtracted. -1 squared is 1. And -4 times -1 is +4. And so whenever I have a double negative, I know that that's the same as a positive. All right, so let's 1 plus 1 is 2, plus 2 times 1 is a +2, plus 4 minus 8. So 2 plus 2 plus 4 is 8, and 8 minus 8 is 0, just as our graph told us. This was one of the possible zeros, and sure enough, 2 is a 0 of this. All right, let's check out +2, which we could see our graph told us was a 0. Now, if you don't have a graphing utility, then you would just start testing these possibilities. And once you find, because this is a 4th degree equation, once you find 2 of these, you're going to be able to write this. You'll be able to find the other 2 without testing. And you don't know if all the roots are rational. Some of them may be and we see that they're not. In other words, you would have tested positive and -1. You would have found -1 worked, +1 didn't. You would have tested positive and -2, and you would have found that +2 worked. And that would have been good enough, actually, for you to stop. Even if some of these other ones worked, you would have had an easier way to find which ones worked. And I'll also show you another method that you would use to test. All right, so I'm testing 2, which I know is really going to be a root because the graph actually told me that. But I'm just really trying to convince you in case I have any unbelievers. All right, so raising 2 to the 4th minus 2 cubed plus 2 times 2 squared minus 4 times 2 minus 8 gives me 16 minus 8 plus 8 minus 8 minus 8. And obviously, -8 plus 8 adds to 0. And I'm left with 16 minus 8 minus 8, which is 16 minus 16, which of course is 0. So we have verified that -1 and 2 are actually rational roots. The rational roots theorem told us that, and the graph told us that. And now we've used algebra to confirm that. I want to show you how we're going to use synthetic division here. First of all, we want to write all the coefficients of our function. And notice that if there were any missing powers of x, we would fill those coefficients in with 0. So say, for instance, you didn't have an x cubed term. in the place of the x cubed term, you would need to put a 0 if that were a missing term. In this case, we have all powers of x. We have power of 4, power of 3, power of 2, power of 1, and a power of 0. So if any of those are missing, you do need to fill those in with zeros in synthetic division. All right, so our coefficients are 1, -1, 2, -4, and -8. 1, -1, 2, I thought it was -4, and -8. So we fill in all the coefficients of the polynomial. If any terms are missing, you do need to put a 0 in that space. All right, now remember the first 0 was -1. And we're just going to go through synthetic division here. So I bring down this first coefficient of 1. I multiply that by -1. I put that product right under the next coefficient above my horizontal line, and I add to get -2. -1 times -2 is 2. I add that, put that product underneath the next coefficient above my horizontal line, add to get 4, put the sum under the horizontal line. -1 times 4 is -4. Put that under the next coefficient, which is -4, add, and I get -8. -1 times -8 is +8. I add these to obtain 0. So what this does is this tells me this polynomial, x to the 4th minus x cubed plus 2x squared minus 4x minus 8 can actually be written as x minus -1, which is the same as x plus 1, times x cubed minus 2x squared plus 4x minus 8. So this gives me a factorization of this. So this is one way you could have done the problem to test. So this is how you would. So what we're doing here is actually unnecessary, but this is how you could have tested your, when you go back to that list of rational roots, synthetic division can be used to test those roots. Or you can test those roots by substituting those in place of x in the function and seeing whether or not the outcome is 0. So you could have used either replacement of x with the root, seeing if the result is 0, or you could have used synthetic division, seeing if the remainder is 0. So both of these processes isn't necessary, one or the other. So now what I'm going to do is I'm going to take the coefficients that resulted from my synthetic division, and now I would test, and I don't use the remainder. Now I'm going to test another possible root. So if I didn't know from the graph that -1 and 2 were the only rational roots, I would test +1. Then I would test, if that didn't give me a 0 remainder using synthetic division here, then I would go and test the next root. But because I use the graph, I'm going to go straight to the next number that I know is a root, and that's 2. So I'm going to notice what I'm testing 2 on. I'm testing it on this polynomial that is a third-degree polynomial that resulted from my previous synthetic division. So I'm going to bring down 1. 2 times 1 is 2. I'm going to place that right under the next coefficient in this synthetic division setup and add, and I get 0. 2 times 0 is 0, so I put that under this next coefficient of 4, and I add. 4 plus 0 is 4, and now I'm going to multiply that by my 2. 2 times 4 is 8, and I put that under the coefficient of -8, and I add, and the result is 0, as I knew it would be, since I knew 2 was a root of the original function. I know that 2 also has to be a root of this polynomial, which is 1 degree less than my original polynomial. So what does this tell me? That's the important thing here. This tells me that x to the 4th minus x cubed plus 2x squared minus 4x minus 8 equals x plus 1. So I'm just carrying down the previous factor times, since I see that 2 is a root, one of my theorems told me that x minus 2 has to be a factor of this polynomial f of x. So I'm using that theorem here. And now I'm using the synthetic division to get a second degree polynomial. So notice x squared, so these give me the coefficients of this lesser degree polynomial. I started with a third degree polynomial. Synthetic division results in the coefficients of a second degree polynomial. Notice that 0, I only use this if 0 is my remainder. If 0 had not been my remainder of the synthetic division process, then 2 would not be a factor. So this is x squared plus 0x plus 4. So we don't want to write terms like 0x when we're writing our factorization. We'll leave 0x is just 0. We'll leave that unwritten, and we'll simply write x squared plus 4. So now I have the polynomial written where the highest, in a factored form, where the highest degree factor is 2, and I can always find the solutions to a second degree polynomial. So here I'm going to merely use the square root property. So I take x squared plus 4 and set it equal to 0. If I subtract 4 from both sides, I see that x squared equals -4. That means, and let me use colors here, using the square root property tells me that I can drop this exponent of 2 on the left if I apply plus minus square root to whatever's on the right. That's the square root property. So it's a trade-off. If I want to get rid of this exponent of 2, okay, but the cost of that is on the right side of the equation to apply plus or minus square root to whatever's on the right. And then we have to remember that the square root of a negative 4 is 2i. So we have to remember that's plus or minus the square root of 4, sorry. Plus or minus square root of 4 times the square root of negative 1. And the square root of negative 1 is I. The square root of 4 is 2. So x is plus or minus 2i. So now this allows me to further factor my polynomial. So I've got the 4 roots of this polynomial. So the polynomial that I started with, x to the 4th minus x cubed plus 2x squared minus 4x minus 8 can be factored into x plus 1 times x minus 2 times x minus 2i times x minus negative 2i, which is x plus 2i. And actually, let's write, this is typically how, if we were going to write the factored form, this is how we would write it. But I want to show you how our theorem applies here. So let's go in and let's write all of these as subtractions. And remember, our leading coefficient of this polynomial is 1. So if we go to the theorem that we covered in the beginning, the linear factorization theorem, if we go here, we actually see that we are fulfilling this theorem for that polynomial. Okay, so what we've done here is we've written this polynomial in factored form. And remember that factored form from our theorem stated that our polynomial could be written as a sub n times x minus c1 times x minus c2 x minus cn. And in this case, since our polynomial was 4th degree, I'm going to go in and I'm going to change these coefficients, these subscripts, to match our particular problem. Okay, so for our particular problem, since our polynomial is 4th degree, n is 4. And notice that a sub 4, the leading term of our polynomial, is an unwritten 1, since our leading coefficient is 1. Okay, so remember, there's actually a 1 here that's unwritten. That's actually our a sub 4. Our C1, in the order of that you write these in doesn't matter, as long as one of your roots, in this case, since we've written this one first, I'm going to call it C1, is negative 1. As long as one of your roots is 2, it doesn't matter if you call 2 C1 or C3 or C4. Since we've written it in second position, I'm going to refer to 2 as C2. Our C3 is 2i, and our C4 is negative 2i. So we fulfilled this for this problem. And you know what? It would have been nice if I would have lined these up. So let me take a minute and do that. Okay, so those are our roots. And notice that the order that you write the roots in doesn't matter. And why is that so? Because it doesn't matter what order we multiply in. You can multiplication is commutative. That means 2 times 3 is the same as 3 times 2. So it doesn't matter which one of these factors you put first. And just to actually write the form, I'm going to put our a sub 4 in here, which is 1. And remember, that's an unwritten 1 in this particular problem. So let's put that in there to show that we have fulfilled this format for this particular problem. The other thing I want to talk about is Descartes' rule of signs. Let's go back to that theorem for a moment. And let's look at that. So here's Descartes' rule of signs, and let's look at that for this problem. So the number of positive real zeros of f is either the same as the number of sign changes or less than the number of sign changes of f of x by a positive even integer. If f of x has only one variation in sign, then f has exactly one positive real zero. So let's go take a look at f. Remember, this is our f. And let's look at how many sign changes f has. So you're looking at sign changes. So the leading coefficient is positive. The next coefficient is negative. So that's one sign change. This coefficient is negative and the next one is positive. That's a second sign change. We go from this positive coefficient to this negative one. That's a third sign change. So the last two coefficients are negative, so that's no sign change. So we have 3 sign changes. So let's look at 3 sign changes for f of x. So let's look back at that theorem and what it tells us, or the rule and what it tells us. So Descartes' rule of signs tells us that we'll either have, for this polynomial, we'll either have 3 sign changes, or we have 3 sign changes, so we'll either have 3 positive real zeros, or we'll have 3 minus 2 positive real zeros. So in other words, for this polynomial, The only possibilities are that it has 3 positive and let's actually just go ahead and put them together. 3 or 1 positive real roots. Those are the only possibilities. So it either has the same number of positive real roots as f of x has sign changes, or it has less than 3 roots by a by an even positive real number. So let's go back to that theorem, that rule. By a positive even integer is what I'm saying. So the first positive even integer is 2. 3 minus 2 is 1. So either we have 3 or we have 3 minus 2 positive real roots. The next positive even integer is 4, but if I subtract 4 from 3, I get a negative number, and I can't have a negative number of roots. So the number of roots has to be 0, 1, or positive. So in other words, this polynomial has either 3 or 1 positive real roots. Now let's talk about the sign changes for f of negative x. So let's talk about that. And remember, f of negative, first let's just talk about f of negative x real quick before we talk about the sign changes for it. Let's talk about f of negative x. So f of negative x is the 4th power applied to negative x minus the 3rd power applied to negative x plus 2 times negative x squared minus 4 times negative x minus 8. So we want to simplify that. So whenever I raise a negative to an even power, the negative is going to become positive. Whenever I raise a negative to an odd power, the negative is going to remain. The negative sign is going to remain. Whenever I raise a negative to an even power, the negative sign is going to disappear. So the square of negative x is just x squared. And here, 4 times negative x is negative 4x. All right, so let's go in and look at this. Let's simplify these double negatives. So this becomes x to the 4th plus x cubed. You still have the power of 3 here, but this is now negative x cubed instead of the cube of negative x. So that becomes a positive x cubed plus a 2x squared plus 4x minus 8. And so you'll see here that all coefficients are positive for the first, second, third, fourth terms, and only the 5th term is negative. So f of negative x has one sign change. There's only one time the sign changes. Now, according to Descartes' rule of signs, for the number of negative real zeros, the number of negative real zeros of this of f of negative x is either the same as the number of sign changes in f of negative x, or less than the number of sign changes in f of negative x by a positive even integer. So in other words, that means if f of negative x has only one variation in sign, then f has exactly one negative real zero. And notice that then clarifies how many positive real roots I have. So once I get this possibility, I'm able to narrow down the possibilities for the number of positive real roots. So f of x has exactly one negative real root. Of course, we already know what it has, but if you didn't know, this rule of signs by Descartes would allow you to know I'm either going to have 3 positive real roots or 1 positive real root. I'm either going and my only possibility for negative real roots is that I have 1. I have 1 sign change in this polynomial, so I have 1 negative real root according to Descartes' rule of signs. All right, and so basically I have all of the solutions. I'm trying to include all of the concepts from this section in this by applying everything to this problem. Notice that I have done way more work than the problem requires, just so I can show you all of the concepts. So the solutions of the equation, x to the 4th minus x cubed plus 2x squared minus 4x minus 8 equals 0 are, and I'm going to put them in a set because that's typically what Mathematica is going to ask you to do. Negative, and I mean my math lab, -1, 2, 2i, and -2i. Those are your 4 roots that solve this equation. And so we've looked at the main ideals from the section in this one problem. Notice that just by using the graph of the function, you save yourself a lot of work. So I actually did way more work than would be required because using the graph eliminated a lot of work. But this is how you apply the theorems and Descartes' rule of sign to this particular problem.